Okay, so welcome everybody to the first session. This is the complexity session in case you didn't notice. And our first speaker is DJ Chen. Is going to talk to us about de-randomization, so please.
Hello everyone, I'm very happy to present my joint work with Xinrui from Tsinghua and Ryan Williams from MIT, which is almost everywhere circuit lower bounds from non-trivial de-randomization. So first, let me give you some motivations on why we want to study almost everywhere circuit lower bounds. So for a function f from Boolean strings to 0 and 1, we use f sub n to denote the restriction of f to n-bit inputs. And also for let's say to be a collection of functions, we also use c sub n to denote the restriction of c on n-bit functions. For example, C could be AC0 circuits and or low degree F2 polynomials, etc. And we'll study two different notions of lower bounds. The first one is called infinitely often separations, and we write it as F not in C. It says that there are infinitely many n such that F sub n is not in C sub n. And the other notion is called almost everywhere separation. It says that F is not in infinitely often C. And it means that for every sufficiently large integer n, it holds that F sub n is not in C sub n. So compared with the infinitely often separations, clearly the almost everywhere separations are stronger. For example, we can look at the famous result by Williams saying that there's a language L in NX such that L is not in AC0. This implies NX is not in AC0. But however, this is only an infinitely often separation. So it could be the case that L is only hard on extremely rare input lengths. For example, it could be the case that L is only hard when n is the power of a power of 2, while L is easy on other inputs. So practically in this case, it seems not very different from L being easy. Since 1980s, a series of circuit lower bounds were established via combinatorial or algebraic approaches. For example, a beautiful line of works proved that the parity function is not in AC0 by random restriction, and the Raspberry and Smolensky proved that the mod 3 function is not in AC0 parity using the famous polynomial method. And here, AC0 is the constant depth and or not gate circuits, and those gates are of unbounded fan-in. And the AC0 parity is the AC0 circuits extended with mod 2 gates. Those type of lower bound methods you usually extend to the almost everywhere setting naturally because they consider each input length separately. But however, they are often subject to the natural proof barrier and they only yield relatively weak lower bounds. For example, so far, we don't know how to use such arguments to prove lower bounds for AC0. There are some attempts, but still it's not clear how to do it. On the other hand, in structural complexity theory, lower bounds against stronger circuit lower bounds are known. For example, in the 80s, Cannon proved that NP to the NP does not have fixed polynomial size circuits. And later, Sutherland proved the same thing for the MA with 1 bit of advice. The same also applies to the Williams lower bound that NX is not in AC0. And this is proved by the algorithmic method and will be today's focus. Those type of arguments usually argues for different input lengths simultaneously because they usually work by some sort of proof by contradiction. And it's not notoriously hard to extend them to the almost everywhere setting. For example, proving that NP to the NP does not have infinitely often linear size circuits is still open. So now let's take a closer look at the algorithmic method. It's a framework to prove circuit lower bounds first developed by Williams. The most well-known result from this method is that NX is not in AC0. The main spirit of this method in one sentence is that non-trivial circuit analysis algorithms can imply circuit lower bounds. So what's the circuit analysis algorithms? The input to them are just a circuit C of n-bit inputs. And we will consider three canonical problems. The first is set, and the set is asking whether there's a satisfying input X. And the sharp set is asks you to count the number of satisfying inputs. And the cap just asks you to estimate the fraction of satisfying inputs within an additive error. By non-trivial, we mean the algorithm should be slightly faster than the 2 to the n brute force time, because you can always enumerate all possible inputs. So in this work, so previously, all such connections only gives you infinitely often lower bounds via the algorithmic method. But in this work, we extend we extend most of the previous results to the almost everywhere setting. So formally, we show that suppose we have a C-set algorithm for n-bit inputs and the polynomial S-gate C circuits in 2 to the n over superpolynomial time. Then this implies e to the np does not have Sn size C circuits for almost every n. So this is an almost everywhere lower bound on e to the np from algorithms for C. When take C to be sub-exponential size ACCC of threshold circuits. And also, suppose we have a sharp C set algorithm or C cap algorithm in 2 to the n minus n to the epsilon time for 2 to the n to the epsilon gate circuits. Then this implies e to the np cannot be half plus 1 over 2 to the 1 over sub-exponentially approximated by sub-exponential size C circuits for almost every n. More formally, there's an f in e to the np such that for all but finitely many n, every S of n size circuit C fails to compute Fn on more than such number of inputs. So using the aforementioned connection, we can extend all previous e to the np lower bounds proved via the algorithmic method to the almost everywhere setting. So as said before, we can easily get strong average case AC0 lower bounds. And secondly, we also extend the e to the np lower bounds for probabilistic degree to the almost everywhere setting. We show that there's an e to the np language L such that for all but finitely many n, Ln does not have little o n over log n squared degree probabilistic F2 polynomials. Similarly, we extend and improve our previous e to the np correlation bounds for F2 polynomial. We show that for all epsilon greater than 0, that's an e to the np language L such that for all but finitely many n, L sub n cannot be half plus 1 over 2 to the n to the omega 1 approximated by n to the half minus epsilon degree F2 polynomials. Finally, there are two recent papers giving p to the np, giving infinitely often p to the np constructions of rigid matrices, and we extend them to the almost everywhere case. We show that there's a p to the np algorithm A such that for all but finitely many n, A will output an n by n matrix Mn such that it's far away from low rank matrices of such rank. So finally, let me discuss the extension to the average case in detail. So by Chen and Ren, there's a function f in quasi-NP such that for infinitely many n, every AC0 circuit of polynomial size cannot half plus 1 more polynomial approximate f sub n. And we show that There's an e to the np function f such that for all sufficiently large n, f sub n cannot half plus 1 over sub-exponentially approximate by sub-exponential size at those circuits. And this is proved by a new XOR lemma. We show that suppose there's no polynomial size linear combination L of C circuits. So L is a weighted sum of many C circuits, and L is a real valued function for F such that L approximate F within a small L1 distance, say 1 over 10. Then XOR of K copies of F cannot be half plus 1 over S approximated by size S C circuits. And we apply this to obtain the new strong average case lower bounds. So after this work, we left with an interesting open question. Can we further show that NX is not in infinitely often SA0? In this work, we only showed for e to the np, and it seems new ideas are required to settle the question for NX. Thanks. Any questions?
Okay, so let's thank the speaker. And any questions? If you have questions, please ask them on Slack. In the chat. Okay.
Oh yes, someone asked that is there a middle ground between infinite often and almost everywhere hard? Yeah, so I think that's a notion called robustly often separation, saying something like the so it means that if a function is robustly hard, it means that the hard input lengths are not polynomially far away. So something like it cannot be extremely sparse. So that's called robustly hard or some robustly often separations.
But do you expect this to be easier?
I think it's easier. It's easier than almost every separation because it doesn't require the function to be hard on all input lengths. Now it only requires the hard input to be not too far away. So it's like somewhat dense in some sense.
Yeah. Any more questions? Don't be shy.
Can I ask a follow-up?
Yeah.
Thank you. So my question is there a case that if I can prove that the function is infinitely often hard, very, very often, then at some point I can easily turn it into almost everywhere hard?
Yeah, sure. For example, if the function is hard on all powers of 2, then I guess you can use some padding to construct an almost everywhere hard function, right? For example, you can just suppose you have like 8 inputs, 10 inputs. You just use the first 8 inputs to as the input of some smaller function. But the point is that this doesn't work when the yeah, so I guess my answer is that is yes. So, then they are just becoming equivalent to almost everywhere separations.
Yeah, if the function has structure, then like paddable, then.
Any more questions? So maybe where you can start setting up. So Jay, can you please close your?
Oh, sorry.
So in a nutshell, what would you need to do to recover the earlier results with an almost everywhere version?
Oh, so yeah, I didn't get time to talk about techniques. So actually we construct a refuter for some version of non-deterministic time hierarchy. So the proof is not hard, but it requires some new insight into the proof structure of the previous proof. And so previously the bottleneck was the lack of the so previously the final step of Ryan's approach is to contract. Oh, sorry. Sure.
No.
Oh, so previously the final step is to contradict the n-time hierarchy, but we don't have an almost everywhere n-time hierarchy. So we come up with some different approach. Yeah.
Mm-hmm.
Oh, so okay. Actually, Roy is going to give a talk. Yeah, maybe I should stop.
Okay. Okay, so let's take the day again. And now Roy is going to give a talk on the explanation of time hypothesis and the randomization. Go ahead.
And circuit lower bounds. Can you hear me?
Yeah, excellent.
Perfect. Hi, everyone. Thank you very much for joining. My name is Roy Tel. This talk is held on exponential time hypotheses. These are plural hypotheses, the randomization, and circuit lower bounds. And this is a joint work with Li Jie-Chen, who just spoke, and with Ron Rothblum, and with Eilon Yogev. And as context, our starting point is the ETH, exponential time hypothesis, which essentially says that 3-SAT takes 2 to the epsilon n time to solve, where n is the number of variables, and there's a linear number of clauses, and there's some epsilon. And this is an exponential version of P is different from NP. It's an exponential separation of P from NP because it says that a specific NP problem takes essentially exponential time to solve. And I'd like to distinguish it right off the bat from the strong exponential time hypothesis, SETH, which says that the lower bound is essentially 2 to the 0.99n for K-SAT, where K is sufficiently large. And I'm distinguishing it because I don't care about SETH in this talk. I only care about the weak version, which asserts a lower bound of 2 to the epsilon n. And a natural extension of ETH is the RETH, saying that essentially the same lower bound holds for randomized algorithms. Randomized algorithms take time 2 to the epsilon n to solve 3-SAT. And this is an exponential version of a separation of NP from BPP. It's an exponential separation of NP from BPP. And along the same lines, we can consider other exponential separations of classical complexity conjectures. For example, a couple of years ago, the non-deterministic ETH was suggested. And this is an exponential separation of co-NP from NP. It says that co-3-SAT can't be solved by non-deterministic machines in time 2 to the epsilon n. And you know, we can do this all day. We can take any classical complexity conjecture and consider an exponential version of it. And they have been considered in the last years. For example, an exponential separation of co-NP from AM, or an exponential separation of sharp P from P. And to be very clear, as far as we know, all of these exponential time hypotheses, ETHs, this is where the plural comes in, as far as we know, all of these ETHs might be true. There is, Ryan Williams refuted a strong version of MAETH several years ago, but that's the strong version, and these are the weak versions. And they look reasonable, some of them even look very appealing, and currently we have no evidence against them. And these ETHs have been broadly influential in complexity theory. For example, they've been used to define complexity classes based on conjectural hardness. This is structural complexity. Have then been useful in communication complexity and tied to parameterized complexity and to fine-grained complexity. They've been very influential. And in this talk, what we're going to focus on is the connection of these ETHs to the field of de-randomization and circuit lower bounds, which is a very natural connection to consider. And in a gist, what we will show is that even very mild ETHs have far-reaching consequences on the world of de-randomization and circuit lower bounds. So in other words, when we assume these ETHs, which we've been accustomed to, we're actually also assuming a whole lot about what's going on in the randomization and circuit lower bounds. And this will be proved via results that are each of independent interest for questions that have been studied for a very long time. And in this talk, I'm going to present just 2 main results from the paper. Each one I'm going to just describe the result in context, and in that I'm going to very briefly mention several other results in the paper. So let's turn to the first main result, which deals with RETH, the randomized exponential time hypothesis, and says that under RETH, BPP can be simulated in almost polynomial time, on average. So on the left side, we have a lower bound for probabilistic algorithms, and on the right side, we we have something that looks almost like BPP equals P on average, almost. It's a strong, very strong randomization result. So this result is in the line of works that's called hardness to randomness. We take a lower bound and we transform it to a de-randomization algorithm. And in particular, this result belongs to the line of force called uniform hardness to randomness, where we start with a lower bound for uniform algorithms, in this case for BP time, and we transform it to an average case de-randomization of PPP. And in contrast to the more well-known line of works for like a non-uniform hardness to randomness, in uniform hardness to randomness, our results are currently lacking. Our knowledge isn't complete, and we have very large gaps. So let's quickly chart a plot. This is a plot of the hardness versus the randomness. So on the x-axis, we have the lower bound. And as we move to the right, the lower bound becomes stronger. And on the y-axis, we have the de-randomization time. And as we move to the bottom, the de-randomization becomes faster. And this is what we'd like to prove. Stronger lower bounds give stronger de-randomization. But prior to this work, the known graph looked approximately like this. So as we start, when we take stronger lower bounds and do get faster de-randomization, but at some point this stops. Even if we take stronger and stronger lower bounds, we don't get any improvement in the de-randomization. And this part here, where the line is flat, is called the high-end part, where we want strong lower bounds and getting fast de-randomization. And in particular, observe that our ETH is somewhere here. It's a very strong lower bound. We expect to get a very fast randomization, but we don't get it. And this gap for the high-end setting has been long-standing, and there have been various previous ways to bypass it. For example, to move to a non-deterministic setting where we can prove things more easily, or to use an inherently stronger hypothesis, like SETH, the strong exponential time hypothesis, or hypothesis from fine-grained complexity. Or perhaps to encounter that this specific challenge must be met in this specific way. And in this work, we resolve almost all of the remaining gap. So we do prove that much stronger lower bounds yield much faster randomization, almost up until the very end. And in particular, let's state the first theorem just a bit more formally. Our assumption is that TQBF, the totally quantified Boolean formula, which is the p-space complete problem, can't be solved in nearly exponential time, 2 to the n over polylog n. And this assumption is weaker than RETH. RETH implies this assumption. And our conclusion is that every language in BPP admits a deterministic algorithm, A sub L, that runs in, this is what I call almost polynomial time, n to the polylog log n. So there's a double logarithmic here in the power. And this deterministic algorithm solves L in the following sense. Every polynomial time sampleable distribution hits a bad input with only negligible probability. So this algorithm looks correct to all polynomial time sampleable distributions. And if you're a bit concerned about the parameters, the n over polylog n here and the polylog log n, let me mention that when you look closely at the hardness of RETH as a function of the input length rather than as a function of the number of variables to the formula, this is the correct hardness and the correct running time that you expect to get from RETH. All right. So this is what I meant when I said that RETH implies an almost polynomial time randomization of PPP on average. Now turning to the second main result, it refers to NETH. And in particular, loosely speaking, it says that NETH implies what I'll call the equivalence conjecture, which is what I now want to describe. So now I need us to switch context to a non-uniform setting. So this is circuit lower bounds and worst case randomization of PPP. And we already know a smooth trade-off in this non-uniform setting. For circuit lower bounds and worst case randomization, the graph that I showed earlier is complete, nice, it's a descending line. But are circuit lower bounds also necessary for worst case randomization rather than only sufficient? So again, as I just said, we know that circuit lower bounds imply the randomization, and we know that the randomization implies weaker circuit lower bounds. For example, Impagliazzo and Regretson show that if E is hard for exponential size circuits, then promise BPP equals promise P. And Murray and Williams recently showed that if promise P equals BPP, then NP is hard for circuits of size n to the 100, or n to the k for every fixed k. But the lower bound on the right-hand side is weaker than the lower bound on the left-hand side. And the equivalence conjecture said that it's essentially an if and only if. The randomization of promise BPP is equivalent to specific corresponding circuit lower bounds against E. For example, E is hard for exponential size circuits if and only if promise BPP equals promise P. And similarly, you can scale this to all sorts of de-randomization times and corresponding specific circuit lower bounds. This is just a particular example. And the importance of the equivalence conjecture is twofold. First, it says that two fundamental questions in complexity theory are the same question in disguise: circuit lower bounds and de-randomization, which a priori do not look like the same question at all. And secondly, it says that there is a canonical black box way of doing the randomization via PRGs. If we can do the randomization in any way, we can do it via PRGs. And the second main result, which I'm not going to state formally, says that a weak version of NETH implies the equivalence conjecture, and we show a partial reverse implication. So this gives appealing evidence that the equivalence conjecture is true. And also it gives a sufficient and in some sense necessary path to prove it. And since the formal theorem involves technicalities, I'm not going to present it in depth, but let me just mention briefly that this weak version of NETH involves lower bounds not for NP, but for n-time uniform circuits, which are like a seemingly weak subclass of n-time Kapko n-time. So to wrap up, we show that RETH implies a very strong de-randomization, and we saw that a weak version of NETH implies the equivalence conjecture. And briefly, I mentioned that if we go up to MAETH, then it's easy to show that under METH, circuit lower bounds hold, and we get a worst-case de-randomization of BPP, and essentially the main questions in de-randomization and circuit lower bounds are answered. So going further up, the ETH hierarchy already gives very strong answers in the world of de-randomization and circuit lower bounds. And for the last slide, let me briefly say a word about a couple of other results in the paper. The first theorem with de-randomization extends to an almost everywhere version, which has been a long-standing gap there. The second theorem about the equivalence conjecture scales, but non-trivially, like not in the same way, but to various other parameter regimes. We show that randomized algorithms for circuit sets that run in time mildly faster than brute force imply non-trivial circuit lower bounds. And in a result that seemingly has nothing to do with ETH, we show a new Karp-Lipton style result, where a collapse in the non-uniform world of circuits leads to a very fast simulation of BPP. And that is it, everyone. Thank you very much for listening. I should look at Gather now, shouldn't I?
No, you should look at Slack. So let's take a
Slack,
break.
yeah, I'm sorry. Yeah.
Yeah, so you went a bit over time, so we have time maybe for one quick question while Mark sets up.
I don't see any questions actually on Slack. Oh, from
Question.
Can you get a polynomial time de-randomization under a stronger variant of RETH? Thanks, Shuichi. So, okay, RETH asserts a lower bound that's slightly sub-exponential in the input length. And I interpret Shuichi's question as saying that, okay, if we assume an exponential, like a truly exponential lower bound for uniform probabilistic algorithms, can we get a purely polynomial time de-randomization? And the answer is no. This is the last gap that we left open in the chart that you saw. This is the rightmost part. And moreover, since you asked, thanks. And since you asked, I'd also like to mention that an even more important gap left in our results in terms of uniform hardness to randomness is that we need the hardness to be against p space, essentially, against a function in p space, TQBF, which is similar to previous results. But ideally, we would like the lower bound to be against e, be against time 2 to the n. And this seems to require new ideas. This is a great open problem.
Okay, so let's thank Lee again.
Thank you.
And now Mark is going to talk to us about lifting.
Yeah, thanks, Yuval. So I'm Mark Vinyals, and I will talk about lifting with simple gadgets and applications to circuit and proof complexity. And this is in work with Susanna de Rosende, Or Meyer, Jakob Nordstrom, Tony Pitassi, and Robert Robert. I will start by talking about the applications to proof complexity part, more precisely about the cut-in planes proof system, which is used to certify that Boolean formulas don't have solutions. So more precisely, you start with the formula in CNF, and you can translate that into a system of linear equations. Now you get a polytope, and the points in that polytope correspond to points in the solutions of the original CNF. Now we can add more inequalities to this polytope, and as long as we don't cut any points from the polytope, well, that is a sound thing to do. So for instance, we can add some inequalities together, we can divide them, and we can keep doing so. And if at some point we reach a contradiction of the form 0 greater or equal than 1, well, that means that the polytope was empty, so the original CNF didn't have any solutions. All right, so this is a cutting plane certificate. Now, what do we want to know about these kinds of certificates? Well, for one, we would like to know about their length. So the length of a proof is just the number of lines in it, number of steps. And it's not too hard to see that any formula that has n variables has a cutting planes proof in length 2 to the n. And there are also some formulas where an exponential length is actually needed. Then we are also interested in the space or memory. So the space of the proof is the number of lines that the verifier that's verifying the proof needs to keep in memory at the whole time. And somewhat surprisingly, it turns out that for any formula, there exists a proof that just needs to use space 5. And finally, we also care about the weights of the proof. So and that's looking at the proof, what's the largest coefficient that appears in the proof, and that's what we call the weights. And it's not, again, too hard to see that we can always prove any formula just using weights, at most 2. However, we might be paying a hefty cost for that, because by insisting on having very small weights, it might be that now the length of the proof has to blow up. And this is in fact something that Buzz and Claude studied back in 96. They proved that, well, we don't need to despair if we have exponentially large weights. Well, that is enough to preserve the length of the proofs with at most a polynomial blow up. But very naturally, they ask, well, can we do better? Can we prove this just using polynomial weights and preserve the length of the proofs? And well, I would say this is unlikely, but for the next 20 years after this result, we didn't know anything, any proof in proof complexity where having large weights would be any good. And that's until some 5 years ago, when a couple of results came in that actually use large weights to do something. But note that I'm saying use here. So sure, these results use large weights, but we still don't know if they are really needed to do something. So our result is about that. We show that there is some situation where having large weights can be is not only useful, it's actually needed. And recall these 3 measures that I mentioned. We had the length, the space, and the weight. And now imagine that we have 2 proofs, one that has small weights but large space. This is one over here. And the proof that has small space but maybe large weights. And my question is, can we get the best of both worlds and get the proof that has both small space and small weight? And of course, we don't want to blow up the length too much. And what we prove is that, well, there are some formulas where this is impossible, and there's a region where no proof can exist. Maybe a bit more formally, we show that, yeah, there's some formula family that has these two kind of proofs, but the product of the three measures must be large. All right, so that's everything about the application. Now I want to talk about the lifting part a bit. But for that, I need to explain at a very high level how we prove this result. And I'll have to use some terms that I won't define, but don't worry too much about the names. I will say what the properties that we need are. So the proof is just the sequence of reductions. So we start with a cutting planes proof. We translate that into a communication protocol. We translate that into a null still inside certificate, which is a simpler object. Then we translate that into an even more simple object, strategy for a table game. And then we use known results for table games to get a contradiction with the fact that we started with a cutting planes proof that was too efficient. So step number 2 is the one about lifting, the one that goes from communication to null still insats. And step number 3 is also new, but I will not talk about it. Great, let's see lifting then. Lifting is a very general technique for proving communication complexity lower bounds using lower bounds from simpler models of computation. And the idea is as follows. We start with a function f over some variables, and then replace every variable with a function or gadget. So in this example, what we would get this composed function that is potentially harder than the original function f. So now what the lifting theorem says is that if you can prove that the original function f is hard in some simple model, queries degree or something else, then we get communication complexity lower bound for the composed problem f composed g. Great, so now let's see how does this apply to us. Recall that our communication protocols actually come from one previous step, which is where we start with a cutting planes proof and get a protocol. And it turns out that if you start with a low weight proof, then you will get a deterministic communication protocol. While if you start with a proof that uses high weights, then you will get a randomized communication protocol. And now, well, since we want to separate these two, if we are to use lifting for this, well, of course, we want to have this composed problem to be hard in the first case, low weights, but easy for randomized communication. And now this is a problem because all previous, or not all, but many of the previous lifting theorems use gadgets such as indexing or inner product that are just too strong. And then the composed problem will be hard for randomized communication as well, which is no good. And our solution is to prove a new lifting theorem that happens to work with simpler gadgets. And in particular, it works with the equality gadget, which satisfies all the properties that we require from it. So a bit more formally, we prove that the deterministic communication of some composed problem is lower bounded by the null still insats degree of the original problem. Doesn't matter too much what this means exactly. And to end, I want to mention the other applications we have, the ones to circuit complexity. We have two applications, in fact. One is to prove a strongly exponential separation between monotone circuits and monotone formulas. So we have an exponential of n over log n over here, while the previous separation was something like exponential of square root n. And we are also able to prove a separation between monotone Boolean formulas and a generalization of that's called monotone real formulas. So to summarize, we proved a new lifting theorem that works with simpler gadgets. And because of that, we were able to prove that large weights are actually needed in cutting planes. And we also had some applications to circuit complexity. Now, where do we go from here? I will just give an open problem that's actually the same one that Buzz and Claude gave in '96, which is are large weights needed in cutting planes, but without talking about space now, just talking about length and weights. Are weights important in that case? And thanks for listening.
Okay, thanks, Mike. Any questions? Don't be shy. Then maybe Massimo has a question. Okay, I'll start. So I guess Mike already stated my open question, but what kind of lifting theorem would it take to solve your open problem?
Right. So for that, we would need some DAG-like lifting theorem. So there are versions of lifting theorem that work not only for normal communication protocols but for DAG-like protocols. And yeah, so one would need to use a lifting theorem like that. But a previous step for this would be to have a lifting theorem that is a bit more constructive, that from a communication protocol, it should give us something a bit more interactive, like a decision tree, except that the decision tree won't work. So yeah, the current lifting theorem is very algebraic in one shot, so we would need something that we can work more easily with.
Okay, there's a question in the chat. Do current results imply separation? Yeah, you see the question?
Yeah, I'm reading it now.
Can you read it also, please?
Yeah, do current results imply separation for tree-like cutting planes versus cutting plane star, which is cutting planes with small weights? And we do get a kind of a separation, but where the upper bound is for semantic cutting planes. So that's a version of cutting planes where you can you don't have any rules. You can just derive anything that follows from through previous inequalities. And yeah, the question, we tried to have an upper bound for the normal kind of tree-like CP, but we didn't manage to do it.
Okay, more questions. So you mentioned that your lifting theorem works with an equality gadget. Does it also work with other gadgets?
Yeah, in fact, it works for any gadget where the rank of the communication matrix is large enough. So with the equality gadget, the communication matrix is identity, so it has full rank, it works great. And any gadget that has enough rank will also work.
Okay, so maybe you can stop sharing screen to let the next talk set up while we think of any further questions. Do you think there's any prospects for applications to other proof systems?
Potentially, there are some proof systems that are defined as anything that that has an efficient communication protocol, so it would apply to those proof systems. But for the more kind of standard proof systems, I'm not sure.
Okay, any more questions? I see Jakob has an answer in the chat, which is also good. Yes, so if there are no more questions, let's thank Mark again. And we still have a few seconds left until Dipanshu begins his talk, assuming he's the speaker. She's the speaker. They're the speaker. Yeah. So the next talk is about formula complexity in relation to tree depth.
Yes, thank you. Can you hear me all right?
Excellent.
Okay. First of all, a very happy Diwali to everyone who's celebrating. We just had it this past weekend. And so I'm Dipanshu, and I'm going to be talking about the formula complexity of the subgraph isomorphism problem and its connections to this graph parameter known as tree depth. This is joint work with Ben Rossman. Right, so let's start off by defining this problem sub G, or the colored G subgraph isomorphism problem, which is the object of study in this talk. So say you have a graph G. In this problem sub G, you're given as input a graph which is known to have the following structure. Right, so all vertices in this input graph, they belong to one of these color classes. There's one color class corresponding to each node of G, and all the edges in this graph, they go across color classes, so corresponding to an edge of G. And every color class contains at most n nodes. And the question is there a properly colored copy of G contained in this graph? So kind of like this. And the models of computation that we're interested in circuits and formulas. So I'm going to define them again. Okay, so why is this problem interesting? From a complexity viewpoint, it contains a special cases, these problems, right? So when G is the clique of size K, this is the same as the K-clique problem, whose complexity is tied to the P versus NP problem. And when G is the path of length K, which I'm calling PK, it's also known as the ST connectivity problem, whose complexity is tied to the NC1 versus P problem. And we have all these circuit lower bounds. So restricted circuit lower bounds, monotone and AC0 lower bounds, known in the special cases of sub G. But what is known about the general, what is known about the complexity of the general problem sub G? Right, so let's talk about the upper bounds first. So you have these circuits of size n to the roughly 3-bit, which happen to be monotone as well as AC0. And you have formulas of size n to the tree depth solving sub G. So I haven't defined tree width and tree depth. We'll see those in a moment. But the point of this this work, the objective is to sort of obtain matching lower bounds, at least in these restricted settings, right? So in the circuit case, this problem was tackled by this work of Lee, Vasper, Rossman a few years ago, who showed that restricted circuits solving this problem require size that's n to the roughly tree width of G. And what we show is basically a complementary result for formulas. So we show that AC0 or monotone formulas solving sub G require size n to the tree depth to 1/3. So a polynomial in the tree depth in the exponent. And of course, what's conjectured is that the unrestricted circuit complexity is n to the tree width, and the unrestricted formula complexity is n to the tree depth. This would separate P from NP and this P from NC1. All right, so what are these parameters, tree width and tree depth? So I won't go into the definition too much, but it's simply a parameter which tells you how tree-like your graph is. So for any tree, it happens to be 1. So it's defined using some tree decompositions. And tree depth is a parameter that tells you how star-like the graph is. So it happens to be 1 for union of stars. And again, I won't go into the precise definition too much, but just as an example, so for the clique of size K, it happens to be K. For the complete bipartite graph K, NN, it happens to be N. And for the path of length K, it happens to be log K. This is for 7, it's 3. and they satisfy this relationship, right? So so obviously you have the formula size of sub G is at least the circuit size of sub G, and correspondingly you have the tree depth of G is at least the tree width of G. So just to state our results again. So first, let's see the Lee-Raspberry-Rossmann again. So they show that the circuit complexity of sub G, the restricted circuit complexity of sub G in these settings is n to the roughly tree width. And we show that the formula complexity of sub G, again in these restricted settings, is n to the roughly tree depth to the 1/3. Yep. Okay, so let's talk about graph minors. So a graph minor is, right, so for a graph G, if you can remove certain edges and contract some other edges, the graph that you land at is called a minor. So in this case, this triangle would be a minor of graph G. And what's relevant to us is that the two parameters, tree width and tree depth that I just spoke about, they happen to be minor monotone. Right? So what's that mean? It means that if f is a minor of G, then the tree width of f is at most the tree width of G, and the tree depth of f is at most the tree depth of G. So how is this helpful? Well, we have this graph minor approximation theorem for tree depth, right? So what that tells us is that any graph that has tree depth that's at least k cubed, it satisfies one of these three, right? So either the tree width itself is kind of large, or it contains a path, or it contains tk, the complete binary tree of height k as a minor. So, right, so how is this useful, right? So we want to prove lower bounds, formula lower bounds for sub G, right? So of course, G could be absolutely anything. So you want to reduce it to certain special cases. So this theorem, it really allows us to do that. So in the first case, the circuit lower bound of Lee-Raspberry-Rossmann immediately yields this formula lower bound. In the second case, this formula lower bound was worked out a few years ago by Rossmann. And this third case was left open, and this is really the content of our work. So yeah, just to state it again, we show lower bounds for sub tk. And we obtain it actually in the average case settings. Right? So here's the input distribution for which we obtain it. Yeah, so let me talk about lower bound proof techniques. So the main technique is this lifting theorem from a result of Rossmann, which is also known as the path set framework. So here's the main idea. So in order to prove formula lower bounds, restricted formula lower bounds for average case sub G, you basically reduce formulas, convert them into these combinatorial objects that we call joint trees with graph G. And then you prove lower bounds on a certain simpler complexity measure defined on these joint trees. And then somehow this lifting theorem tells us that these simpler complexity lower bounds, they lift to the formula lower bounds, solving sub G. Right? So what are these objects joint trees? So they kind of look like this. So these are simply binary trees whose leaves are labeled by edges of G, and they sort of combine at the internal nodes to give rise to subgraphs of G. And the way that our lower bound really works is by proving this sort of a lower bound, a lower bound on a certain potential function, phi. And this phi is defined on all joint trees. Right? And this phi is, it's defined using these couple of rules. And the whole game is to use these two rules somehow to obtain a linear lower bound for all joint trees, right? And this was really the fun part, because at this point we've abstracted out all the formula complexity details, and now it's the proof it becomes entirely combinatorial. And then we have a couple of supplementary results. So these are about formula upper bounds for average case sub pk. So in the average case version of sub pk, you have this sort of a layered graph, and you include any edge across layers with probability roughly 1/n. And the problem is to determine if there's a path that goes all the way across. And turns out there's very simple n to the log k De Morgan formulas. And using a sort of a blocking technique, you can obtain these n to the half log k formulas. And so for a while, we thought that this was actually optimal. But yeah, eventually we found out that you can actually improve it. So we were able to do that using these Fibonacci patterns that are described in more detail in the longer version of the talk, if you're interested, and whose formula complexity turns out to be something to do with the golden ratio, and they beat the n to the half log k. So that was something else that was interesting. And so, okay, so let me just end by mentioning a couple of open problems. So, right, there's still this gap for the formula complexity of the average k sub pk problem. So as we just saw, the improved upper bound is it's n to the log k with the square root 5 plus 2 in the base of the exponent. And then another result of our work shows a lower bound with square root 5 plus 5 in the base of the exponent. So you'd like to close this gap completely. And then obviously it's open to improve the formula lower bound from this tree depth to 1/3 to just tree depth in the exponent. And then such a result cannot rely on the graph minor approximation theorem for tree depth that we saw, because we know that there has to be a loss if we use that. And yeah, let me stop here.
Okay, so let's thank Dipanshu. And Dipanshu, maybe you can go one slide back to the other problems. Yeah, thanks. Okay, any questions?
I'm sorry.
Maybe yes.
Can you please clarify why you cannot get the, maybe it's obvious, I don't know, but why you cannot get the improved lower bound using the minor theorems and this kind of reasoning?
Oh, so it's it's got to do with the fact that there's a k cubed there, right? So yeah, so yeah, this k cubed, I mean this 3 in the exponent is why we have the tree depth to the 1/3 as well. So, well, if you had something like an omega k here, then I guess it would have worked out. It's really because of this. So is your question why you cannot improve this theorem itself to something better than k cubed?
Yeah, why not?
Because you have counter examples for that. So you can construct graphs whose tree depth is, let's say k squared, which satisfy neither of these three.
Okay.
Yeah, but maybe you can add like other cases to account for that.
Yeah, maybe. Right. So
well, maybe you can improve it a bit, but yeah, I understand you cannot close the gap here.
Exactly. Yeah.
Okay. Thank you.
Any more questions? So maybe it's not really a question to you, but how complicated is this structural result that you rely on?
Sorry, say that again.
Yeah, how complicated is this structural result that you rely on?
Oh, it's. I mean, it's another paper, so I guess it's fairly complicated.
But it's not nearly as complicated as the grid minor theorem for tree width, if that's what you're asking.
Yeah. Well, that's a very high bar. Okay, so Dipanshu, maybe you can stop sharing the screen to let Susanna have some time to set up.
Yep, sure.
Meanwhile, if anybody has any other questions. Okay, so if not, let's thank Dipanshu again.
All right, thank you.
And we still have a few seconds, but meanwhile, I can introduce the next talk, which is also about lifting. But this time the application, instead of being proof complexity, it's going to be KRW. I'm sure Susanna will tell us what it is. There's still a few seconds, so yeah, maybe I should have learned stand up or something. Yeah. Okay, so Susanna, please.
Okay, so yeah, so this is going to be about lifting, but applications to the KRW conjecture. And this is joint work with Orr, Jakob, Tony, and Robert. So as usual, we're interested in understanding how hard it is to compute functions. And here, the model we'll be looking at is our Boolean circuits. So we have OR and NOT gates. And for this talk, we'll be only considering fan-in-2. And the complexity measure we're interested is in the depth, so the depth required to compute the function. That's the depth of the shallowest circuit that computes the function. And it's not hard to see that if f is a function that depends on all variables, well, we need depth at least log n to compute it. And that's because we're only considering fan-in-2. So there's a natural question, well, what are these functions that can be computed in close to the smallest step possible? So this is the class NC1. And does this class actually contain all functions that can be computed in polynomial time? Or can we actually prove that there is some explicit function that requires depth little omega of log n? And it's surprisingly hard to prove depth lower bounds. The state of the art for over 20 years is almost 3 times log n. And since then, there's only been improvement in the little o of 1 factor. So in order to attack this problem, Karshma, Raz, and Vigderson proposed an approach. And so what they proposed is that, what they showed is that it's enough to understand composition of functions. So what I mean by composition, so we have 2 functions here, f and g. F has arity m, g has arity n. And the composed function is simply substituting the input variables of f by an independent copy of g. So this is the f composed with g. And if we would like to construct a circuit that computes this composed function, there's a very easy way of doing this. We can consider a circuit that computes f, and in the place of the input variables, we add circuits that compute g, and in this way we have a circuit that computes f composed with g. So by this, it's very easy to see that the depth required to compute the composed function is not more than the depth required to compute f plus the depth required to compute g. So the KRW conjecture is saying that this circuit is essentially optimal. So for every non-constant functions, that the depth complexity of the composed function is approximately additive. And what KRW showed is that this conjecture, if we could prove this conjecture, we would prove that P is not equal to NC1. I'll just point out here, this approximately equal is intentionally vague because there are different definitions that would give this implication. But essentially, this is what we're trying to prove, that composition behaves like this. So what is the state of the art with regards to the KRW conjecture? We know how to prove this for any outer function f, but only when composed with 2 specific g's. And here is where we hit a barrier. How can we extend this to more inner functions? So this is where our results come in. So this is our motivation. We would like to extend the KRW conjecture to hold for more inner functions. And the problem here is that the way the KRW conjecture has been shown to hold, it requires a very good understanding of the depth complexity of the inner function. And there are not so many functions for which we do understand their depth complexity so well. So it seems that we don't have so many good candidates where we could try to extend the KRW conjecture. Well, at least not in the non-monotone world. So in the monotone world, we do have several functions which we understand their monotone depth complexity very well. So we consider the monotone KRW conjecture. And I'd like to point out that it's interesting in its own right, and it's still open. So if we would like to prove the full KRW conjecture, it's a very good place to start. Can we at least prove the monotone KRW conjecture? So we show that it holds for any outer function f when composed with any inner function such that this inner function lower bound follows from some lifting theorem. And I'd like to point out, I won't have time to talk about exactly what this lifting theorem is, but it includes classical inner functions such as ST connectivity, click, or the gen function. So it's basically any monotone function for which we know how to prove a lower bound except for matching. So this was our first result. So we were able to extend the range of inner functions that we can handle in this monotone setting. But in order to get closer to the non-monotone setting, which in the end, that would be our ultimate goal, we propose a semi-monotone model. And I think this definition is also a very nice contribution of this paper. It can be a way of bringing us from the monotone to the non-monotone KRW conjecture. And in this semi-monotone model, we show that the conjecture holds for the universal relation composed with any inner function such that we can prove the lower bound of the inner function via lifting. So this universal relation, well, we can think of it simply as a simplification of a function. So this is it's a simplified version of the semi-monotone KRW conjecture. So that's what we're able to prove. And okay, so just yes, summing up. So the KRW conjecture is promising approach for proving that P is not equal to NC1. And we can extend the range of inner functions to include ST connectivity, click, and the gen function in both the monotone setting for any outer function, and in this new semi-monotone setting, but in the setting only for the universal relation. And then two open problems. So one is to prove the semi-monotone KRW conjecture for every outer function, and not only for this in the simplified version. And another open problem would be to prove the full monotone KRW conjecture. And perhaps a step towards this would be to extend the monotone KRW for G being the matching, which is the most notable case we can't handle. And that's it. Thank you.
Okay, thanks, Susanna. And we already have one question, so can you explain again what's the semi-monotone setting?
Right. So I didn't explain that. So the idea is that so here we have the semi-monotone. The idea is that we consider f, the outer function, it's non-monotone, and the inner function is monotone. So yeah, so okay, that's the basic idea. So the KRW conjecture can be reformulated in terms of communication, and in this communication model, the inner function, we require the players to solve the harder game in the monotone setting for the inner function, but for the outer function, it's more similar to the non-monotone setting.
Okay, so there's another question in the chat. So the KRW conjecture separates NT1 from P. Do these other versions, like monotone KRW or semi-monotone, have lead to any similar separations?
Right, yes. So the monotone KRW conjecture would separate monotone NC1 from monotone P, but this is already known. So it wouldn't be proving anything new, but it has the same implication, yes.
And
I don't know about the semi-monotone model, if you would get some, I can't think of it now.
is there any corresponding circuit model? Does this make any sense?
I'm not sure. Not straightforward.
Susanna?
Yeah. Yes.
You have this semi-monotone model in which the inner functions are monotone and the other function are not. So basically, the bottleneck is understanding the inner functions.
Yes.
If you have like the reverse, you will already imply KRW.
So
monotone in the other function and non-monotone in the inner function.
If that would already imply P not equal to NC1?
Yeah.
I don't think so. So what would imply, yeah, so you don't actually have to prove it for all the inner functions. If you proved it for all outer functions when composed with a specific, this multiplexer relation, which is something that Orr has in one of his papers, so that would be enough. It just seems that like the barrier, like what's hard is understanding the inner function, but it's not that the other way around would be enough, as far as I know.
Okay. Thank you.
Yeah, any more questions? Maybe you can say a bit about what does it mean for G's lower bound to follow from lifting?
Right. So there's so again, we consider this the communication problem, which well, the KW game, and there is some so there's some communication problem which we can reduce to this inner function, to the KW game on this on these inner function. So we use two different lifting theorems. So one of the lifting theorems we use is this simulation lifting theorem, which we strengthen it to work in the case where you start off with some initial information. So the players already know some information about each other's input, and then we can still prove the lifting. So that's for one of the theorems, and the other one we use the lifting theorem that Mark talked about 2 talks back, this Nostolinsatz lifting theorem. But perhaps you could generalize this to work for any lifting theorem. So it might, that might be possible.
All right, thanks. Okay, so can you please stop sharing your screen so that Suichi time to thanks? So do you have any kind of abstract theory of lifting in mind? You said any kind of lifting theory.
Okay, yeah. Maybe definitely these lifting theorems that work with like gadgets, where like a simulation kind of lifting theorem. I think those should work. Yeah, not sure if every.
Okay, so let's thank Susanna again. And now for the last talk in this session, we have Soichi Hidahara, who's going to talk to us about meta-complexity.
Thank you. So I'm going to present a characterization of average case complexity of pH by worst case meta-complexity. So there are two mysteries of complexity theory. One is the average case complexity of pH. This question essentially dates back to a similar work of Levin. And an example of the question is whether dist pH is not a subset of average P. This statement means that whether pH is hard on average in the sense of LRX heuristic scheme. Another mystery of complexity theory is the complexity of computing time-bounded Kolmogorov complexity. This question essentially dates back to a similar work of Thierry Coe, and we usually call complexity of complexity as meta-complexity. An example of meta-complexity theoretic problem is whether gap mingative with pH oracle is not in P. This means whether it is hard to approximate pH oracle time-bounded Kolmogorov complexity. These two questions originate from around the 1980s, but previously we didn't know the exact relationship among them. What we do in this work is to establish a link between these two questions. We actually establish the equivalence between these two statements. So what we show is a link between average case complexity and worst case meta-complexity. Our main theorem proves the following two statements are equivalent. One is a statement about average case hardness of pH, and the other is a statement about worst case hardness of meta-complexity. How should we interpret this result? Well, we have two interpretations of this result. From a perspective of meta-complexity, previously we didn't know the complexity of gap mingative with pH oracle. Our result essentially settles the complexity of gap mingative with pH oracle as a dist pH complete problem in the sense of this equivalence. From a perspective of average case complexity, our result provides a completely new proof technique of analyzing average case complexity by using meta-complexity. As a specific application, I'm going to explain a hardness amplification theorem for pH. Because of the time limitation, I will focus on explaining the hardness amplification theorem for pH, and I will not talk about meta-complexity. So let us review the notion of average case complexity. In the average case complexity, we are usually concerned with a distributional problem, which is just a pair of a decision problem, L, and a distribution of instances. And Levin introduced the notion of average case polynomial time, but nowadays it is more common to define average P as the class of LRS heuristic schemes. An LRS heuristic scheme satisfies the following three conditions. Firstly, we require that the algorithm outputs the correct answer, or otherwise the algorithm outputs a special symbol failure, indicating failure. Secondly, we require that the algorithm fails with probability at most delta, where delta is a parameter given to the algorithm. And we require that A runs in time polynomial in n by delta. And I'm going to use the notation average sub delta P to denote the class of LRS heuristic scheme with failure probability fixed to delta. With this notion in mind, let's review the current landscape of average case complexity. And I'm going to explain what's the important open question in average case complexity. one of the most important open question in the theory of average case complexity is whether worst and average case complexities of NP are equivalent, which corresponds to this blue implication. Especially assuming that NP is easy on average with respect to every sample distribution, can we show that P is equal to NP? That's the important open question. And we can consider a similar question in the case of pH. Just a quick reminder, pH stands for polynomial time hierarchy. Another important open question is whether we can get our hardness amplification theorem. For example, assuming that NP is easy on a small fraction of inputs, can we show that NP is easy on most inputs? This question is often referred to as a hardness amplification theorem. We usually consider the counterpositive, but the question is essentially whether it is possible to amplify the success probability of our heuristic algorithms. Another important open question is whether the relationship between one-sided error versus errorless heuristic scheme. I'm going to use a notation average superscript 1p to denote the one-sided error heuristic schemes. And the question, one important open question is whether the one-sided error and errorless average case complexes of NP are equivalent. And we can consider a similar question in the case of pH. And what we show in this work is to prove this implication. This means that if pH is easy on a small fraction of input for one-sided error heuristic, then we can prove that pH is easy on most inputs. As a consequence, we can prove that all these four statements are equivalent to each other. That's a corollary of our result. So let me explain how we prove this corollary. This means that we can prove an errorless hardness amplification theorem for pH against deterministic algorithms. So I'm going to explain how we prove this. What's interesting about the proof is that the proof goes through the notion of metacomplexity. I'm on the top half of the figure, I'm going to write statements on worst case metacomplexity. On the bottom half of the figure, I'm going to write statements on average case complexity. As a first step, we observe that min KT with pH oracle is a problem in pH. I haven't explained the definition of min KT with pH oracle, but this is just a simple observation. Namely, if pH is easy on average, then min KT with pH oracle is easy on average as well. Now, here is an important step. By using a non-black box worst case average case reduction, we can show that this implication. If we have an average case polynomial time algorithm for min KT with pH oracle, then we can prove that there is a worst case algorithm for gap min KT with pH oracle. And then we can go back to the average case complexity statement by proving this pH hardness of gap min KT with pH oracle. This implication can be proved based on our previous work. What I would like to emphasize, so this established the corollary, because by just combining all three implications, we get the red arrow. What's interesting about the proof is that the proof goes through the notion of metacomplexity, despite that the statement itself is just a statement about average case complexity. So to summarize, to conclude this talk, we established a link between average case complexity and worst case metacomplexity. As a consequence, we were able to get a new proof technique of analyzing average case complexity by using metacomplexity. Let's give you one favorite open question. Can we prove that this NP hardness of gap min KT? If we can prove this, we can get a hardness application for NP as well. Thank you for your attention.
Okay, thanks, Luigi. Okay, any questions? So maybe while you're thinking about your question, let me start. So, okay, so we have a question from Adra. Do these results relativize?
Yeah, that's a good question. But most of the result relativize. Yeah, actually it should be relativized, but the current proof in the paper is actually not relativizing because we use the PCP type theorem. But I believe that we can replace, well, I think that's not essential to the proof. So yes, I think our result relativizes.
So is this a place where you said there's a non-black box result? This is what you mean?
Yeah, so the meaning of a non-black box reduction is that we exploit the efficiency of Oracle. Usually, if you consider a reduction, it is black box in the sense that you don't care about the complexity of Oracle. But such a black box reduction have quite a severe limit. So if you just use black box reduction, it is impossible to establish this implication. Actually, there's a barrier result by Bogdan and Torepisen. And actually, we needed to use non-black box reduction to get this implication.
But wouldn't that mean that the results do not relativize?
It's a bit different. Non-black box just means that we use efficiency of the Oracle, but that doesn't, yeah, so let me clarify the meaning of relativize. So this should relativize for any Oracle A if you put A everywhere, basically everywhere. So, well, I guess this is not a standard notion of relativization, but in some sense it relativizes.
Okay. More questions? So if instead of the entire polynomial hierarchy, I wanted to do something inside the polynomial hierarchy, is that possible? Like maybe you assume something on the 5th level and you get something about the 3rd level or the 6th level or whatever?
Yeah, if we have something about the 5th level, we get something about the 4th level. So there is if you go through the equivalence, you lose one level, basically. The reason is here. If you have a min KT with PH Oracle, it is a problem in NP with PH Oracle. So basically you lose one level, basically.
So your point question is essentially to get rid of that.
Yeah, exactly. Yeah, the last open question is whether we can get rid of that. So what we can prove is that if we have NP Oracle, we can prove this. But the question is whether we can get rid of this.
Okay, more questions. Okay, I think probably everybody's tired after an hour and a half of these talks. It's a bit tiring. Okay, so let's thank Soichi and let's thank all the speakers of this session. So you can maybe, more of you can clap and open your cameras. And hope to see you during the next session.